Welcome everyone to the next session. We all love these software updates of our devices waiting for hours, and now we learn from Felix and Jan how we can do that faster.
So making or using Delta updates to make your updates leaner. This is our topic of our talk. So hope no one here has seen our talk already in Seattle. That's good. It's have a little bit of improvements, but in general, it's a similar thing that we already presented at the Embedded Open Source Summit a couple of weeks ago. So first of all, who are we? Felix?
I'm Felix. I work for Siemens Technology as an embedded Linux developer, and I'm lucky because I can do open source both for fun as well as for profit. And I'm involved in the development of the developer tools, so like the CAS tool, for instance, or also tools for dynamic, static code analysis and build systems.
Yeah, I'm Jan Kisker. Also doing that for quite a while at Siemens now, consulting our business units. Some of you may have run into me already regarding Linux usage, maintaining a couple of open source projects, quite a few by now, some of them piled up. Some I have to hand over from time to time. I'm also involved in the CIP project, representative of Siemens there at the TSC. We'll talk a bit more about this. And I love open source for, well, a couple of decades by now, and enjoy doing this here for Siemens. So we heard already about this software update story over the air, and your car, if it's a modern one, probably receives updates already over the air. Your router at home does, and so do also the modern industrial field devices in one form or the other. So hopefully no longer by carrying in the updates, but rather by transmitting it over cable, over wire. And while this is one generic use case, I would say, charging stations for your e-car, they are way more than just doing charging. At least some of them, they are almost entertainment boxes. So these systems, they pile up a lot of large software stacks, and more software goes onto that for various functionality. And if you don't take care, well, you also have to transfer these updates in large chunks to the devices. So this is where we basically start from. This is what we need to have, not necessarily large images, but at least this updatability, because the last thing you want to do is to really run again to these devices and do the updates there manually or reset the devices if they are broken. So as this is a fairly common pattern, we are also taking care of this in a collaboration project. The CIP project I mentioned before, Civil Infrastructure Platform, that now exists for 8 years by now actually, started in 2016 by Toshiba, Hitachi and Siemens. Well, we are doing a lot of things there. You may know us for certain things, but we're doing more. So first of all, the goal of CIP is, so to say, providing an industrial-grade Linux in form of having the key elements for that ready to use. So we are not reinventing wheels. We are building on top of existing open source projects. We contribute to them if they don't fulfill in our domain the needs. Or we create some new ones if there is nothing and no one is so far providing something for us. We provide integration patterns. Well, even if you have all the building blocks around, it's not that easy sometimes to get them in the right form to build, for example, these update scenarios. And then we also address the topic of long life systems. So you may know us for the CIP kernel, the long living kernel. The 4.4 kernel, for example, is now maintained by CIP in the 8th year. And we are maintaining currently 4 kernels, 5 in the end. So this is also an area. And last but not least, we are working on security certification of these base integration so that you can build easily on top and certify your products according to IEC standards in the future. So, and one area of this integration pattern is around software update. So there are 2 work groups dealing with this, directly or indirectly, the CIP core and the software update work groups. So what do we do at CIP core? This is basically our central place where we build the systems and the user land as reference images. We do this here based on, this is where the CIP project agreed on, based on Debian sources. We are using tools outside of the project, the ESA build system. It's conceptually and technically in many cases similar to Yocto at a certain distance, but it's using the Debian binary feed for that integration. So we try to use, so to say, wherever possible, the binary feeds, the upstream feeds, the pre-tested images, and we only deviate where needed. For example, here in the area of this more customized integration procedure. So at the end, you don't have to install your embedded devices. You can do the normal imaging procedure as you're familiar with from firmware production. So these pre-integration images, they define secure, bootable, and updatable reference images. So they're not designed to be something you download and then you install your application on top, you are done. Normally this is more what you do for a product development, but they provide you some kind of a reference image, and ideally it's only that installing of your own application on top, but practically normally it's more customization on top. The concepts we're going to present today, they are implemented and tested in that form of this ESA integration, Debian integration, but the concepts are absolutely generic. So you can transfer them also to Yocto and Open Embedded as well. So we heard about already some building blocks of this before. So Christian and Michael were presenting WFX, and this is the device side, software update. This is where we agreed on in CIP to build upon. This is, again, also not technically not necessarily the only way to implement it, but this is basically where we focus on right now and where we also worked on over the past years to improve it for the use case. The update pattern is reliable. Again, no rocket science. We already heard about from Ardian about the AB update pattern. That's what we use as well. We, in the end, want to have an immutable root file system so that we don't do package-based updates and in the end have something undefined in the field, but rather a pre-tested and well-defined base image that we update here. And the whole thing has to be secure, obviously, so secure boot is in scope. We do that via UEFI secure booting so that we don't have to reinvent the wheel when we go from x86 to ARM or to RISC-V. All of them are supported. SW update comes with image signing. It's a feature to turn on, but in the end you have to have the infrastructure for that, so this is also provided here. We do have disk encryption, obviously, for data at rest. The pattern here is normally that you encrypt the persistent data partition and you keep the root file system unencrypted because they shouldn't contain secrets, shouldn't. In some cases they do. So the CAT pattern we show later on is based on an open but verity protected root file system, but nowadays we have just merged support for encrypted root file system as well, in case you do have secrets in the root file systems. So this is very similar to what we've seen already, a B update pattern. How does it look like? So we are booting coming from the firmware. We are in a B switching bootloader in this case. That selects then a unified kernel image, the way how you do secure booting these days on AFI systems. So you bundle the kernel, the inner RAMFS, possibly kernel parameters, device trees if you need to, in one image that's assigned. And then you boot from there the actual root file system, which again, as I said, is integrity protected or is encrypted. And you have this persistent data partition, which is not updated during the update process, because this is the stable part, the device state, so to say. So these root file systems normally are the bits that you have to update along, sometimes also with the kernel, if you do a firmware update in the field. And they can become, well, if you do it not very elegantly, or if you really have large software stacks, they can become rather large. So what we do right now, state of the art, we generate these root file systems in the build chain, and then we ship this whole root file systems as update artifact, wrapped around and especially described to devices. And that obviously can become quite inefficient. So the question is, can we actually ship only what changed? Now, if you add a package or update a package in this root file system, why not just simply getting this delta, this effective delta transferred? So what do we have to do in order to generate this delta out of the existing and the future version of the root file system? And this is one question, how to transfer it over the air and make sure that all the properties I talked about are still kept. So we do want to have, obviously, the whole thing working still securely. we do want to maintain the reliability of the whole update procedure. And with that question, we started the examination, and I would hand over to Felix now to tell us how this can work.
Thanks, Jan. So the first thing you need to think about when talking about a delta update is how to describe your delta. So you need an algorithm to compute the difference between two artifacts, and ideally the difference is then small if the artifacts do not differ much. So one option you have here is the Z-chunk compression format, which is based on Z-standard, or it technically uses Z-standard compression internally. And it's both a compression format as well as a tool which you can use to then download just the delta from a baseline and the image you want to update. Hereby, the key idea is to have that download process over HTTP and use HTTP range requests. Why range requests? Because they are well supported. All the video providers like YouTube, they already use them to just transfer the section of the video you are currently watching, even if you skip in there. Yeah, it's well supported. Another option you have is to use RDiff, or in general librsync, as a library to generate a difference of two blobs. And the advantage hereby is that you can, they do not make any assumptions how you transfer this delta then. While for that chunk, as I said, the assumption usually is that you download that via HTTP. But here with the librsync algorithm, there is no such assumption. So you can just create a delta and then later on apply that delta. And how you transfer it is not part of the concept hereby. A third strategy, which is mentioned in the Open Embedded world a couple of times, is CA-sync that originates from systemd. The idea hereby was to have an efficient way to transfer test images. It's a combination of the rsync algorithm to compute the delta, as well as a way to address these deltas both on a blob level, block level, as well as on a per file level. It's not considered here because it doesn't really fit into the core concepts of SW update, that you ideally just have one file to describe your update, or maybe two, but not a whole set of files which you need to provide on a server in a particular way. And also there's unfortunately no library to control that. That's why I have it here on the slide for the sake of completeness, but we don't look at that closer. As Jan said, the tool we use for the update is SW update, and SW update itself has the concept of handlers. They describe how to apply the update, among other things, but this is the thing which is important for this talk here. And the first use case we have a look here is the RDiff handler, which performs the delta update based on the RDiff pre-generated artifact hereby. So let's start. The first thing you need to do is to generate your image. Once you have your image, then you need to generate an RDiff signature against the old image. That's the image that is booted on the device. Ideally, you already know that because you go from version 1 to version 2, and you don't need to know what is on the device, but I mean, you know what you put on the device before, so you can compute that delta hereby and just put the delta into the SW update file, which then of course is smaller, given that the delta is also small, and that's it. The SW update file is then the file which is read by SW update to perform the update. The next thing is that you upload that file to a backend. In this case, we call it update server, but for details, I would refer to the talk of Christian. And once you have it there, you basically just do the standard workflow. That means SW update on the device. The service detects that there is a new update available, downloads that update, and then combines it with the old image. Why does it work? Well, we generated the RDIF file just based on what we expect to be the old image and the new image. It's secured by checksum, so we can really see if it actually matches. But if it matches, we just read the old image, combine that with the delta, and write it to the currently not used rootfs partition, because we always operate only on the partitions which are not mounted. And we are done. So a big advantage hereby is that we don't need to change anything in the back end or on the workflow itself, as it's still this only SWU file which we use to transfer the update. Another thing is also we can sign the things up front as we did before. So no matter if we do a full image update or just the delta update, what we sign is just this SWU file here, and this is then checked on the client. And an additional advantage is that we don't make any assumptions about the transport. So it doesn't matter if we download the file via HTTP or if we put it on a USB drive, give it to a technician, and then the technician plugs it in and the update is performed here. Or we can use OPC UA or whatever. It doesn't really matter which transport we use here. But it has a big drawback, and that is we can only do incremental updates, as we need to know upfront what our old image here is, because in the end, that's the delta between the new image and the old, what we put into our update artifact. So we can only do these updates from known states. And also you cannot skip. A slightly different variant of basically the same pattern generates the delta file not up front where you build the image, but on demand in the back end. The advantage hereby is that you can first query the device which version of the image it is actually running, and then generate this delta file based on the new version and the version that is running. This is not implemented in SW Update itself to transfer or to inform the backend about this, the version that is running there, but you can easily implement that. It has the advantage that you can update basically from any version to any version, but you need a bidirectional communication channel between these two. And also, you have a problem with the signing of the SW update file. The reason here is that usually the builder, the image builder here, is not the same entity as the provider of the update server here. Like this could be Siemens or us, and this could be an update server which is running at a customer site. But to make the signing work, then here in the update server, you need the keys to sign the artifact, and by that you have to hand out the keys, which is probably not possible in many use cases. Let's have a look at a totally different approach based on the set chunk handler. Hereby, the workflow is a bit different. So first, what we do is we still start with the SW update file with the whole image, and then we create a block-based, or for some ranges, a checksum file, which does not contain the data, but just hashes or checksums of chunks of the data. This is the so-called Z-chunk image header. This only needs the new version, not the old version. And it's quite small. You can also configure the chunk size, so even for very big images, you still can have it quite efficient. The next thing is you upload the new image, though not the SWU file, but just basically the rootfs partition to any backend. It can be the same WFX update server, but you can also do that out of band. You can also use an S3 bucket for that, as long as you can access that via HTTP. And inside the SWU file, you only put the header. Then you also upload this SWU file with the metadata and the header to the backend. And from there, you perform the standard SW update workflow. That means the device checks if there's a new version available, and then it downloads this SWU file with the image header. Once you have it there, the Delta handler checks which artifacts are already on my device, basically by just reading the block device, and which deltas do I need to download. Now, downloading these deltas on a per block basis is very efficient, very inefficient, but you can improve that by using range requests. That means upfront you check like which deltas are missing, and then you make a range request with exactly the ranges you need to download. Usually that's a single request, but if it's too many ranges, you can have multiple there, but still it's basically as good as you can get. And then the handler combines both the downloaded deltas as well as what you already have on your device and writes that to the new partition. And the big advantage hereby is that you can update from any version to any version. Theoretically, your rootfs does not even need to be read-only, because as long as it's not changing, you can compute everything on the fly. Another advantage is that you still can sign things at build time here, because what you sign is just here, this SWU file, which contains the header and the checksums, and by that the rest of the system is also integrity protected. And you don't have a blow up in size if your delta is quite big. Like with RDiff, I said you have the problem that the delta might get quite big if the delta between both images is big. So like if it's more than 50%, you might even end up with a bigger delta than if you do a whole image update. While here, you're super efficient as you really just download the things you need, but you don't have much overhead for the delta itself. Unfortunately, you're then limited to an HTTP channel between where you have this file here. Doesn't matter if it's in the backend or if it's on a CDN or wherever. And you need a communication path between here, which is somehow reliable. You cannot do an update via USB anymore, as there you cannot do the delta update via HTTP between the USB drive and the image. One very important thing when talking about doing a delta update is to optimize the image building to only change things which really need to be changed. That is much easier said than done. But it's very important, as otherwise your delta gets big, and if your delta is too big, the whole benefit of only updating the delta vanishes, because the difference between the full update and just the delta update is quite small. So when building things, make sure that you can build your packages reproducibly. Reproducible builds has a lot of tips and tricks to how to do that. But it also makes sense to just check if your packages can be built reproducible, and if not, investigate why that's the case, and maybe you can improve that. Second is that if you only can build your packages reproducible, that's not sufficient, as you also need a way to install them reproducibly into the rootfs. Otherwise, if things are scrambled around, although there you generate a big delta. In the civil infrastructure platform, ISOCIP Core, we took extra care to make sure that not too many things change when we install these packages. Then you do a block level or block device update. That means it's not a file-based, a block level update. So you somehow need to assemble a rootfs. And when you assemble that, you need to choose a rootfs which can also be constructed in a reproducible manner. And you even need more. You even need to make sure that if you only have a small delta in the input, also the generated rootfs in the output should only contain a little delta there. One example here for a read-only rootfs is the squashfs. This is usually compressed. And when compressing that, make sure that you use R-syncable algorithms or compression algorithms in rsync mode. as otherwise these compression algorithms take all the state and information they can get to come up with the best possible compression, but by that also the whole output changes, even if you only make a small change in the input. With the rsync flag, the compression state is reset after each chunk. So chunk size can vary, but it's reset from time to time. And by that, chunks that did not change in the input will also not change in the output. And finally, when you create your update artifact, you also need to make sure that you compress that, either that you don't compress it, as basically the biggest part, like the rootfs, is already compressed, or if you compress it slightly for whatever reasons, make sure that you also use R-syncable algorithms with a reasonable chunk size to make sure that then this also, that the delta here also remains as small as possible. How about using that in practice? So in the ISOCIP core project, we already have all required components included. We both support the RDiff as well as the Z-chunk algorithm. It's not yet released, but we have it already on the next branch, and in the next release it will be included. But if you are interested, you can also use it, already use it today. From the SW update components, the SW update project itself has support for both RDiff as well as Z-chunk, which is good for the Yocto people. They are not using ISA, but still they profit from that as we have it in SW update. Then our handlers to technically perform the update also support it. We have support for chaining handlers, like one handler for selecting which partition to update and then the next handler to actually decide how to do the update there. Having a look at the backends, if you go with the RDiff workflow, no difference. So all backends that support the general SW update workflow will also support that workflow. For Z-chunk, the information is a bit different. The situation is a bit different. The Hawkbit backend does not yet support, probably will never support to upload these two images, like the SWU file as well as the Z-chunk compressed rootfs. But if you use another way to store the rootfs, you can make it work. It's just a bit cumbersome. If you go with the WFX backend, it's natively supported. So there it just works out of the box. That's also what we tested against. Some frequently asked questions about Delta updates and security. As Jan said, one of the goals is to not break the security guarantees by only updating the Delta. And for that, it might not be obvious why it doesn't make a difference if we do a Delta update or a full image update. So let me briefly show you why that's the case. So the first thing that is done when downloading the update here is that the signature of this file here, this SWU file, is checked by the client here. And only if it's valid, then the update process continues. That's the same for both the full update as well as for the Delta update. Then, in case of Z-chunk, you have two download paths. One is here for the SWU file. This is pretty standard. It's like before. The second one is here, the Z-chunk image, which you download via HTTP from a URL. But this URL is part of here of this file, so you cannot change it, and by that it's integrity protected. I mean, because it's integrity protected, you cannot change it. If you are concerned about the confidentiality here on this update, on this download path here, you have two options. One is use HTTPS, simple. But if you have more complicated workflows where you might need some login, for instance, to be able to then pull the image, you can even do that by just running a local reverse proxy here, which does all the authentication and token injection stuff, so that you then can just download from the reverse proxy, which secures this path here. And finally, the image that is assembled is bit by bit identical by design with the full update image. and this is DM-verity protected. So even if something for whatever reason would go wrong here, still you can't come up with a valid but tempered image, as then the DM-verity checksum wouldn't match anymore, and by that you cannot mount that, and then you would just fall back into the old one. For the RDIF-based workflows, we don't have to talk about that at all, as the path is exactly the same as with the full image update. Another thing is another question is, why does it work when combined with Secure Boot? And as shown before, basically the first thing we boot is the EFI loader here. In our case, that's EFI boot guard, which is signed with the Secure Boot keys, which are then encoded in added to the platform. This bootloader then selects, based on a configuration, selects the UKI, so that's the kernel which is booted next. And this kernel again is a signed EFI binary, which contains the init.rd, and the init.rd has the checksum for the DM-verity protected rootfs. So if the rootfs would be tempered, then here we would detect it because we cannot mount it, as the checksums wouldn't match. And finally, we also need to mount the data partitions, which are encrypted, and these are encrypted with a key from the hardware TPM, for instance, or a software TPM or whatever. So what did we get so far? Doing a Delta update is usually more resource efficient than doing a full update, and the difference is the bigger, the smaller the delta is. So really try to keep your deltas as minimal as possible, then you profit most of the Delta update mechanism. It's as reliable as the full image update, as shown on the last slides. You don't have any impact on security. All guarantees we give with a full image update, we also still provide with the partial or with the Delta update. But also, like always in life, it's no free lunch. You need to decide for a workflow, and each of the workflows like RDIF or ZChunk comes with their pros and cons. For RDIF, the problem is you need to know the Delta up front, so you can only update from well-known states, or at least you somehow need a way to generate these well-known states on demand. In case of ZChunk, you have the problem that you're limited to this HTTP download path, and you have two artifacts there. So you can't do a pure offline update with a USB drive, for instance. Then finally, I want to say thank you to my colleagues both at Siemens as well as our contributors from Toshiba, who did most of the implementation there, also helped a lot with the review, and especially I want to give a shout out to Wang Qi from Siemens China, who did a lot of testing and review of the whole implementation to really make it reliable. And that's it. I think we still have some time for questions.
Do you have some data on how much do you can compress? So like what the image sizes is and what usually the update sizes are, the deltas?
Yeah, back in Seattle we were asked the same thing. Unfortunately, there's no easy answer because it depends on so many things. Like if you do a full distro update, for instance, probably it does not make much sense to use the RDIF handler because the delta is too big. So in general, for RDIF, the delta is the same size as the full image update once your input delta is more than 50% of the whole block size. So like if you have a 2 GB image and 1 GB is changed, then going with the delta handler does not make sense. And if your delta is even bigger, then it's worse to do the delta update compared to a full image update. If you go with the ZChunk handler, it doesn't matter, so you always profit. That's why for this kind of updates, probably the ZChunk handler would be better. But one thing that is often forgotten is that from a workflow perspective, you still can decide later on if you want to do a delta update or not. You still can upload a full image and the system will happily accept that and flash that, because all the logic to drive the update is included in this SWU file. And by that, if you see that your delta SWU file in case of RDefendler is too big, yeah, then simply don't use it, simply go with the full update.
You mentioned that for setjunk you're using HTTP. Did you play around with HTTP 2 or 3 or like compression on HTTP level? Because that would be an actual benefit that you could put, like directly use from HTTP, right?
No. So let's keep it short. No, we didn't do that. So compression does not make much sense as the things you transfer is already compressed. So why add another compression layer around it? I mean, it's that standard compressed. That means you can cheaply decompress it, and also it's quite well compressed. Of course, you can play around with HTTP options or so, but with the current implementation, with the libsetjunk, you're limited to what this library supports. This is also a problem for us, as we know there are use cases where you don't want to perform your update via HTTP at all. So in the future, we might work on that, or people might work on adding pluggable transports that you can replace that component. Then you're also more flexible in tuning this update path. Other questions?
Thank you for the presentation. Really refreshing and embedded. How do you revoke keys if something gets leaked?
Mm-hmm. So currently this is not in scope for that part. It's, so to say, not an orthogonal topic on top, but it's a topic we also look into. So our project partner Toshiba are currently specifically looking into the TUF framework, the update framework, and trying to use the key management patterns that exist there, looking for a good implementation. So there's some problem on the implementation side, but that's currently the way we try to drive it, to have that aspect also addressed here.
There's another question.
Sorry. Thank you for the great presentation. I'm wondering whether the customer is also using this remote update workflow to do a kind of A/B testing. Like some features can be released, some other features won't be released, and they will observe and the acceptance of some very special versions and before make a bigger decision.
Yeah, again, it depends obviously on your product, if the product has this kind of decision in the process. So there are products, actually there are domains where the customer decides when to do that. Now, the classical topic of the maintenance window. You don't do the update while the train is riding, normally. So there's a maintenance window for that. The customer decides. The customer says, now is the time to shut down my machine. The machine is in, or the train is in the station, now I can do that. You may use that actually for qualifying additional parameters, additional properties of the update in your environment before releasing it, for confirming it. But then again, there are also boxes that we provide where we control it, so to say, as supplier, and we decided upfront, so to say, that we're going to now ship it, and yeah, and it's there. Then it's no interaction. But it's quite common actually. The customer has a certain control, at least on when the update happens. Again, like on your mobile, you usually have the answer or the choice to say, okay, I want to update now, I want to update next night, or please defer.
Maybe in addition to that, usually you try to avoid to roll back. So ideally, I mean, of course, you test that the rollback works, but in the field, that's the rare case that you actually do a rollback or the system rolls back, because then something went wrong which shouldn't went wrong in the first place. And that's why, in my opinion, this is not really suited for A/B tests. It's more like, yeah, you can do that during testing, but in production you would probably never do that.
The rollback contains, besides the rollback of the core images that we have shown here, that's the easy part, so to say, at least from a distance perspective. It contains the rollback of your own state. And that's normally the case which is not tested. Now you do maybe the forward update of your device state and test this heavily, and then you forget about, okay, what if this goes wrong and I go back? Then I'm with the new data, with the old image, and now I'm stuck. And now you have a service case in the field. That is not that easy to achieve. I've seen some solution. We still want to work on this, but it's also no easy answer to give you, nah, this is the pattern for it. No, there are end patterns. Depending on what you have to update there, sometimes the database contains mechanism for that, then use it. Sometimes it's your own invention, then you, well, have to deal with it. And then there's the area in between. And this is not that trivial in practice. So we've seen devices who went only the one way.